Good morning. We are wrapping up DC circuits, maybe today, maybe next class. I just updated the calendar, so we're going to sneak in. We're going to finish up DC circuits either today or Friday. Monday is a holiday. I removed that class that was listed there on the calendar. I think we're okay on timing. If we have to make something up later on, we'll worry about it when we get there. So no class on Monday. We have a 3-day weekend ahead of us. And then the next class would be a Wednesday next week. That would be new material. We'll start magnetic fields then. We'll have our exam on Friday, a week from this Friday, whatever date that is. And then, and it will not cover the new material, will not cover magnetic fields, only up through chapter 10, DC circuits. The 29th, exam on the 29th. Lab next week. Do you want to cancel it? So what we've got 8 labs. We've got 10 weeks. So 2 weeks, no labs. I guess we could do one. Why don't we do skip next week, and then we'll skip the last week of the quarter. How does that sound? Next Friday, a week from Friday. Okay, so no labs next week, and then we'll also skip the last week of the quarter for labs. Give you a little extra time to catch up on whatever you need to catch up on. Okay, very good. So today we are going to do a quick discussion of charging, discharging capacitors. I know you've already had your lab on that, and hopefully you understand that. But we'll do a quick. We hadn't covered it yet in lecture, so we'll do a quick coverage of charging, discharging capacitors, and then we'll just work some problems. Probably that's the main thing we'll do today. So we've got a resistor, we've got a capacitor, we've got a switch, we've got an EMF source. Switch open, no charge on capacitor. No current flowing. We close the switch. Current begins to flow. The capacitor begins to charge. So this is just after the switch is closed. Current flows. Capacitor begins to charge. And then a little while later, what happens? The capacitor is charged. This is, I'll say, after a long time. Okay. So we were interested in this brief time here in the middle, right? What's happening at this brief time in the middle when current is flowing and the capacitor is charging? And you have to read physics problems carefully. We're using capacitors right now in DC circuits. So there's not a lot that can happen there. It's you were either interested in the case where the switch is just closed and the capacitor kind of acts like a short, or we're interested in the case when the switch has been closed a long time, the circuit's been hooked up for a long time, and the capacitor has reached some steady state and no current flows in the branch that has the capacitor. So we can use a loop rule for this circuit. We can use a loop rule for any circuit, right? And what the loop rule says is the sum of all the potential rises and drops as you go around a loop, when you get back to your starting point, has to be 0. So we go up through the battery, we rise by the EMF of the battery. We go through a resistor, we've dropped now by IR. And now we go through a capacitor. Q equals CV for a capacitor, so V is equal to Q over C. So we've dropped by Q over C, and now we're back at 0. Both Q and I vary in time. And we can write I as dq dt. Right? That's the current is the change in charge over time. So we can rewrite this equation. And substitute in, this is dq dt. And you want to get all the q's on one side. And of course, your math instructors don't like this, but physicists do it all the time. We multiply both sides by dt and integrate. And so we end up with all the q's on one side. You get your dq over here. It's a differential equation.
I think math professor does that as well.
Oh, okay. They tell us they don't like it. And what do we get? The solution to this is the natural log of, I'm not going to work out all the details here, but you get the idea. We're solving a differential equation. And so we want to get Q as a function of time. That's the objective here. We want to know what's the charge on that capacitor as a function of time. How is that changing in time? So it's going to equal its maximum charge times 1 minus e to the minus t over RC. And the current in the circuit, if we were to look at current, now we didn't look at current in our lab, that we would have used the voltage on the resistor, right, to get the current. But it follows the exact same equation as the charge on the capacitor. So I felt it wasn't necessary to do both. This is I maximum, e to the minus t over RC. All right, so you get these exponentials, right? It's either a rising or a decaying exponential. And just make sure you have the right one. So when you're charging the circuit, it starts out, when you're charging the capacitor, I should say, it starts out with 0 charge on it. So put t equals 0 into your equation, make sure you get 0 for Q. And the current in the circuit is the biggest because there's no charge on that capacitor. It acts like a short at that instant. The current is the biggest. As the capacitor starts to charge up, let's look at our circuit. As the capacitor starts to charge up, it almost acts like a battery pushing back in the opposite direction, right? And so it slows, it makes it harder to flow charges through the circuit because you're trying to push the charges onto a capacitor that already has a bunch of charges on it. If I plot these, we get our Q as a function of time. This is Q max. And your current does just the opposite, right? Starts at maximum and decays to 0. Okay. And we talked about the fact that we want to compare circuits. I make a circuit, you make a circuit. We want to be able to compare them. And because it takes an infinite, according to the math, it takes an infinite amount of time to completely charge or completely discharge. That's not helpful to say, well, how long does your circuit take to charge? How long does your circuit take to discharge? Everybody's circuit takes an infinite amount of time. So let's pick some other number. Let's pick how long does it take to get to half of its maximum charge, or how long does it take to get to some other value? Well, a really nice value is 1 over E of its maximum value, or 1 minus 1 over E in this case, because this is a charging capacitor. So we just set T equal to RC. When T is equal to RC, then we're at this nice special value, 1 over E of its maximum value. In this case, it's 1 over E. In this case, it's 1 minus 1 over E. So we use tau, time constant of the circuit. Okay. And you could go through discharging the exact same way. There's no EMF source, right? Your circuit is a little simpler. You've got your capacitor, your resistor. Now it starts out fully charged, and you close that switch and current flows while it's discharging. And then it goes to 0, right? Okay. And we get, I'm not going to go through the whole thing here, but we get the slightly different equations now. Q as a function of time is Q max e to the minus t, that's a minus sign. And the current in the circuit where that is, what is I max? It's Q over R. Is that right? And the direction, this just indicates direction of discharging current is opposite charging current. All right, so I went through it fairly quickly. Hopefully it was a review. We've gone through it already in the lab lecture and in the lab. But the idea is that with DC circuits, typically we're concerned with the switch is just closed and we treat the capacitor like a short at that point. Or the switch has been closed for a long time, the circuit's been hooked up for a long time, and then the capacitor is an open circuit, no current flows through the branch with the capacitor. This deals with the little bit of time in between there when current is flowing, and we want to know how much current is flowing in the circuit at a particular time. One application here is the intermittent windshield wipers on your car. So you want to be able to set your windshield wipers so they just go once, wait a few seconds, they go again, wait a few seconds, they go again when it's not raining very hard. So you set up a circuit. And you make this a variable resistor. That arrow through it means it's a variable resistor. You can change the value of the resistance. And then you hook up the motor for the windshield wipers across the capacitor. When the windshield wipers get the voltage they need, they go. And that drains the capacitor. The battery charges up that capacitor. As soon as it gets to the right voltage, the capacitor discharges through the windshield wipers, causing them to go. And then it takes time to charge back up again. And you can change the time by changing the resistance in the RC circuit. So it's a relatively simple design, but it makes the those intermittent windshield wipers work. Oh, because it's not discharging through the resistor. So this resistor is large, and it gives you a large, it gives you a long time constant, right? Because you're charging through the resistor, but you're discharging through another mechanism that doesn't have that. It takes the current very quickly and releases the motor. All right, let's do this one. Oh, this is number 1 over here. This is ammeter 2 over here. And voltmeter. I'm missing a voltmeter. Voltmeter over here also. This is 2. And this is voltmeter 1. Okay, so tell me what each of the meters reads. These are ideal meters. How are we doing? Okay. So let's trace the current path. The current would take this path from the battery. Would it go through voltmeter V1? No. Ideal voltmeters have infinite resistance. So it wouldn't go through there, but it would go through a 1 ohm resistor. Now, there are 3 parallel paths to get to the other side. One path is through voltmeter V2. That has infinite resistance, so it can't take it there. One path is through the ammeter, and one path is through the 2 ohm resistor. So remember, we said if there's some resistance in every path, some current will take every path. But if there's a 0 resistance path, all the current takes the path of 0 resistance. And in this case, an ammeter, an ideal ammeter, has 0 resistance. So all the current takes the path of 0 resistance, and then it goes back to the battery. Basically, the 2 ohm resistor is shorted out. So we've got 4 ohms of resistance in this circuit and a 12-volt battery. So I is 3 amps, and it's going through both ammeters. Both of them are going to read the same. V1 reads the voltage drop across I1, so we can multiply the current times the resistance, and we get 3 volts. And V2 is shorted out. By the ammeter, it reads 0 volts. Should we check this? Let's see if my circuit is still here. All right, so this is my circuit. I have, let's see what values we've got here. I've got a 1 ohm, a 2 ohm, and a 3 ohm resistor, 12-volt battery. I've got my ammeter here and here, ammeter 1, ammeter 2, and a voltmeter hooked up across over here in parallel with the ammeter, and then I can move it to the other location. They only lets me put 1 voltmeter in for some reason. So let's hook up the circuit. We've got current flowing. Nothing is going through this resistor, this 2 ohm resistor, because it's shorted out by the ammeter. There's a 0 resistance path there. Current is 3 amps. The voltage across the ammeter is 0. And if we move this to the other side here, we get 3 volts. I would hook it up this way, though. 3 volts. Very easy to check what you're doing with these. Okay. Each capacitor in this combination has a breakdown voltage of 15 volts. What's the breakdown voltage of the combination? If you put 15 volts on any one of these, the dielectric breaks down, the capacitor becomes a conductor, it's no good anymore. So a maximum of 15 volts on any single one of these capacitors. So what can you apply out here? What voltage can you apply between these 2 points to the whole thing? What's the maximum voltage you can apply between points A and B? We don't want them to break down. We're trying to find that point just before they break down, I guess. Not quite. If this capacitor has 15 volts across it, then this one also has 15 volts across it. They are in parallel, and the same with this set over here. So let's combine these. Let's redraw this. We've got A over here. And B over here. And we've got our 10 microfarad in the middle. And what do we have on each end? So Q1, Q2, Q3, but what do we know about those Qs? Okay. Which one of these three is going to be the first to break down? The 10, yes, the middle one. Because they all have the same, right? As we increase, we've got our voltage power supply hooked up to points A and B, and we're turning up the voltage, right? 1 volt, 2 volts, 3 volts. As we're turning it up, how does that split across the three capacitors in series? Well, they all have to have the same charge. Q equals CV. They all have to have the same charge. So the one with the smallest capacitance is going to have the biggest delta V across it. The one with the biggest capacitance is going to have the smallest delta V. So as we crank this up, it's going to split, the voltage is going to split, and most of it is going to be over the 10 microfarad capacitor. Less is going to be over the 40 microfarad capacitor. So we'll set that equal to 15 volts and work our way out and see what VAB has to be to make that 15 volts. Did you solve for Q first and then use that to work your way out? <clears throat> 150 microcoulombs on each of these capacitors. We okay with this one? Ready to move on? Okay, find the current in each resistor and the potential difference between points A and B.
Do we use the Kirchhoff rule for this problem?
If you need to.
I'll be just guessing.
No, you are solving. This one, you need Kirchhoff's rules, right? It's as simple as you can. You can't simplify it anymore using your series and parallel rules. And so there's enough 3 unknowns, but you can get them with Kirchhoff's rules. Let's just set up the equations. Let's just set up the equations for now. I'll call this I4, and I'll pick the direction of the battery. Usually the current goes in the direction of the battery, right? I'll call this one I6. And since the 12-volt battery is bigger than the 8-volt battery, I'll guess that the current's going to the right through the 2-ohm resistor. I'll call that I2. So I've guessed my directions of the currents, and I can come up with a junction rule. I4 is equal to 2 plus 6. Now we need 2 loops. I'll start in the lower left corner. Let's see, I'll use green. Start in the lower left corner, and I'll just do that, and I'll call that loop 1. First thing I do when I go around, walk around loop 1 in that direction, I go in the low side of the battery, I come out the high, I raise my potential by 8 volts. Then I go in the high side of that resistor, I come out the low, I drop by I6 times 6. Then I go around and I get to the 2-ohm resistor, but I'm going in the low side, coming out the high. I'm going opposite the current. So I'm rising by the current times the resistance, and I'm back to where I started. And I'll use blue now. I'm going to go around the perimeter of the whole thing. Call that loop 2. Remember, you have to have a junction. Can't use 3 loops. So 2 loops and a junction. The loops have to have something that's different and something that's the same. So if you're going with the current, remember, if we pick the current as going this direction, then the left side has to be at higher potential than the right side, or the current wouldn't be going in that direction, because current is positive charge flow. Positive charge flows to lower potential with the electric field, in the direction of the electric field, to lower electric potential. So when I'm going around my circuit, if I go with the current, I'm dropping by potential. If I go opposite the direction of the current, I have to rise by that potential. So it starts out the same way. And then I get up, I pass point B. I'm going in the direction of the current. I'm dropping by I4 times 4. I am rising by 12 volts, and I'm back to where I started. Now, I solve these, so you don't have to do it right now. If you know how to use your calculator, then you can double check my answers. I got I2 is 0.909 amps, and I4 is 2.549, and I6 1.64. If only there was a way for me to check my answers. What could I do? I could use a PhET simulation, couldn't I? Let's take a look. Okay, here's my circuit. Does it look like my circuit? I've got a 12 volt battery and an 8 volt battery, a 2 ohm, a 4 ohm, and a 6 ohm. I tried to make it look just like the circuit we're doing. Let's connect these together. There's the current flow. Well, actually, that's the electron flow. We could, if you want to make it the current flow, we could do that. There's the current flow. And let's see, I4. What did I say I4 was? 2.549. So let's put our current meter over here, measure the current through I4. We get 2.55 amps. Okay, 2.55 amps, close enough. And I2, 0.909. 0.91, this meter only goes to 2 decimal places, so it's rounding off to 2 decimal places. And I6, 1.64. We're good. See how easy that is? Set up the circuit, check your results. So let's take a 10-minute break, and we will continue with more problems, circuit problems. Quick question. All right, here we have a circuit with some switches and various configurations. We can figure out what the ammeter reads and the voltmeter. Let's put a voltmeter. Put a voltmeter here. Add that. Okay, so tell me what the meters read. And let's see, what values did I use? And we'll just do two conditions. Let's just do A and G. If you want to do more later, you can do more later. We'll do A and G for now. So do you have the current path for A? All the switches are open. Current comes from the battery. It gets to this junction and it has a choice, right? Well, not really in this case. Two of those paths have open switches. They are infinite resistance, so the current really does not have any path. It has to take this branch, and then it gets to this junction, and that switch is open, so it doesn't really have a choice there either, does it? So that's the path of the current in part A, and it has no other choice. So let me see what I used for current here. Let's see, I used 10 ohms. All the resistors are 10 ohms, and it's a 12-volt battery. So let's make it a 12-volt battery and 10 ohm resistors. Okay, should we check our answers? 3 volts on our voltmeter that I added here, and a current of 0.3 amps. Is that what everybody got? So I've got this set up, all 10 ohm resistors, all the switches are open, 12 volt battery, my ammeter is reading 0.3. My voltmeter is reading 3 volts. Okay. Let's go back and do G. We're going to close 2 of those switches. We're closing, what are we closing? 1 and 2. 1 is up here, 2 is over here. We'll leave 3 open. Close 1 and 2. Did you find the current path? Current comes out of the battery, gets to this junction. One of those 3 parallel paths is an infinite resistance. It's not going to take that. The switch is open in the bottom. And one of them has some resistance, and the other one has 0 resistance. There's a 0 resistance path. There's a short here. So all the current will take the path of 0 resistance. And then it gets to this point, and it says some current can take one path, some can take the other, so it can split. Some will go this way, some will go this way, and it comes back together here. So what do we have? We have our current is V over R, and V is 12 volts, and R is 15. Is that right? Well, we'll find out, won't we? All I have to do is click on the switch, close it. Now there's a 0 resistance path there, and I can click on this switch. I have 0.8 amps and 8 volts. The current path, let's just go conventional current here. Current path through the short, it splits part goes through this resistor, part goes through this resistor, comes back together, and back to the battery. All set. Okay, let's keep moving. All right, we've got a circuit. They're telling us that the ammeter reads 2 amps. They want us to find I1, I2, and the potential on that second battery. Do you have to use Kirchhoff's rules here?
I think so.
I think there's some given information here that will enable us to do this without Kirchhoff's rules. They are not in parallel. This cannot be reduced any more than it is. But what information is given? Current and direction of flow. They're telling us I1 and I2 flow in these directions. So there's only one choice for I3, right? That current in the middle branch. It can't go to the left. All the current can't go into that junction. It has to flow to the right. And they tell us it's 2 amps. Now, can you do it without Kirchhoff's rules?
Yes, sir.
Excellent. All right, so far so good. Once you know the delta V between points A and B, and that's basically given in this problem, A is 10 volts higher than B is. So I can take any path from B to A and I have to rise by 10 volts. I can take this path and I have to go up by 10 volts. So that's what I did here. I went up by 15, I dropped by I times 7, and I have to get to 10 when I get to the other side. That gives me I1. Then I used the junction rule. To get my other current, I2. And now I can use another sort of a loop rule, I guess you could call it. I'm not going a whole loop. You could go all the way around in the loop, but I already know A is 10 volts higher than B. I'm just going to take one path. I know that going up by the EMF of that battery minus I2 times 2 has to give me 10. So my EMF is 10 plus, what is it, 2, about 4.6. Oops, no, 2.6. There we go. So I've got about 12.6 volts. We good with this one?
Good, good.
Part D. We're going to use this answer for our EMF of the battery, and we're going to switch the voltmeter and the ammeter. And you're going to tell me what the 2 meters read. So our circuit now looks like this. Okay. Have you redrawn the circuit? What's it look like? Is any current go through this middle branch?
Nope.
No, this is an infinite resistance here. We can just remove that. There's nothing there. Any current go through this resistor? No, because there's a short across it. We can just remove that. So this is what our circuit looks like. We can redraw that if we wanted to. We've got a resistor, 7 ohms. It's the only resistor in the circuit. And we've got 2 batteries opposing each other. That's like one battery in this direction, 2.4. We good with that? This one was 12.4. This one was 10. What was this, 15? 12.6. That's better. 12.6, 15. So we're subtracting the 12.6 from the 15, and we still have 2.4 pushing current in the counterclockwise direction. Okay. So let's look back. What was the question? What do the meters read? What do the meters read? All of this current is going through that ammeter, right? All of the current is going through the ammeter. So the ammeter reads that current. And the voltmeter, what does it read? Let's get out our pens. Let's call this 0 here, 0 volts. This is going to be 15 volts, right? And what's this going to be? 12.6 volts. But where does it stop? It keeps going here, right? There's no voltage drop there. That's all 0 resistance path. What's the voltage drop across a resistor with no current flowing through it? 0. So that voltmeter, one side of the voltmeter is hooked up to 0. The other side's hooked up to 12.6. It's going to read 12.6 volts. Current is not flowing through the middle branch. I'm not sure what you mean. Current is not flowing through this resistor because there's a voltmeter in series with it. There's an infinite resistance in series with it. So current can't flow through this branch at all. We have to remove that whole branch from our circuit. Current cannot flow through there. There's an infinite resistance in that branch. And current will not flow through this other resistor because there's a short around it. Current will always take the path of zero resistance instead of a path with resistance. So it's shorted out. Okay. All right, we've got the circuit. You're going to rank the potential at points A, B, C, D, and E from highest to lowest. Rank the potentials A, B, C, D, and E. We have a ranking yet? Should we get out our colored pens here? What do we have? Let's make this symbol here tells us it defines zero potential. So we not only can we rank them, we should be able to tell what some of them are, right? Some of them we can give values to. Some of them we would have to solve a Kirchhoff's problem to figure them out. We don't want to do that. So let's just rank them, but fill in what you know. So that tells us that this is zero here. This is zero. Where's my green pen? We have defined that as zeros. Right off the bat, we know one of them. We know E is zero. Then this one up here is, what is this voltage in this section here? We started at zero. We went up through a 12-volt battery, so we must be at 12 volts. And let's go to the other side. What am I calling? How about this one? This color must be at 9 volts. And what's left here? Gray. That has to be, what does that have to be? It has to be more than 0 and less than 9. We good with that? Because current is flowing this way. Why is current flowing that way? Because 9 volts is more than the voltage on the other side. Okay, so we can rank these now. A is the greatest, and it is 12 volts. And then what's next? D is next, is that correct? And it is 9 volts. And B and C have to be the same. And they are greater than E, which we know is 0. Current is flowing from the 9-volt battery through B, through C, and then to E to ground, right? So the current is flowing through the resistor, tells us that one side of the resistor has to be higher potential than the other side. Now we're ready to rank the currents at those same locations. Yeah, you're talking about points B and C, right, Max? Correct, yes. Points B and C are connected by 0 resistance paths, so their potential has to be the same, but there's a junction in between them, so their currents do not have to be the same. Okay, which is going to have the greatest current? That we should be able to spot. Okay, keep thinking about it. We got a 12-volt battery pushing current this way. We've got a 9-volt battery pushing current this way. "12-volt battery, 9-volt battery. Where does all that current go? Through point E. The 12-volt battery's current, the 9-volt battery current, it comes together and it all goes through point E. Point E sees all the current. It has to be the most. Let's take a look at the other two. Well, what do we know about A and B? And what do we know about C and D? A and B have to be the same because they're on the same branch, right? There's no forks in the road. There's no junctions between A and B. A has to equal B. What about C and D? Same thing. So we know A and B have to be equal. We know C and D have to be equal. We just have to figure out which set is the bigger one. Which set is the bigger one? AB. How do we know that? Because these two resistors are the same. Those two resistors are the same, and one of them goes from 12 volts to some potential there, and the other one goes from 9 volts to some potential there, right? That gray potential is the same for both sides. Let's pretend it's 7 volts. I don't know what it is. Let's pretend it's 7 volts in the middle there. One resistor goes from 9 to 7. So you have a resistor with a 2-volt drop across it. So figure out the current flowing there through it. The other resistor goes from 12 to 7. That's a 5-volt drop. It's going to have 2.5 times as much current flowing through it. So A and B are tied with each other, but they are greater than C and D. E is the biggest because you've got the 9-volt battery is pushing some current this way. The 12-volt battery is pushing some current this way. And what do? They come together, and all of it goes through point E. So E has to be the biggest. And then we did the rest with basically with Ohm's law, yeah. Good. One more? Three 60-watt, 120-volt light bulbs are in this circuit. When the switch is open, rank the brightness of the bulbs. They are all the same. Right? They're identical light bulbs. They all have the same resistance. They all get the same current, power. Take your pick. I would look at this one. The resistance is the same for all of them. The current is the same for all of them. The power dissipated has to be the same for all of them. All the same. Now B says we close that switch. What do we get? A and B are still the same type of light bulb, identical light bulb, same resistance. They are in series with each other. So A and B have to be the same. But what happens to C? C goes out, right? It's shorted out. C turns off. Okay, now we're going to continue with the switch closed. We're going to replace bulb A with the 100-watt bulb. Rank the brightness. A is 100-watt bulb, B is a 60-watt bulb. Okay, so we can look at this. This is a good way to write out power. Every time you need power, write it out like that and pick the formula that makes the most sense. So let's compare a 100-watt bulb with the 60-watt bulb. They have to be rated at some voltage. Well, light bulbs are typically used when you plug a lamp into a wall, so they're rated at 120 volts. If we know the voltage and we know the power, we can use this equation to get the resistance. So for our 60-watt bulb, it's 120 squared over R, or R is 240 ohms. Let's move that over a little bit. For the 100-watt bulb, we get 144 ohms. Remember, they're meant to be hooked up in parallel. Every time you put a light bulb in a lamp somewhere, you expect it to get 120 volts. So you expect them all to get the same voltage. Well, why would one be brighter than the other one if you're giving them both the same voltage? Because it has a smaller resistance, it will draw more current than the other one will. But we're not hooking them up in parallel in this circuit, we're hooking them up in series. So which one, if they both are hooked up in series, they're going to have the same current. If they have the same current, let's look at our equation here. The one with the bigger resistor will burn more brightly, will dissipate more power. So that would be the 60-watt bulb. So for case C here, which one's the 60? B would be greater than A. Okay. Was that a good way to finish up DC circuits? All right. I'm going to stop the recording. I'll stick around for a little bit if there are questions. And then don't forget, we've got office hours also, but I'll stick around, see if there are any questions.
Question.